moment. Well, thank you everyone for joining us today. This is a very exciting seminar that we're pleased to present on best practices for cabling and test leads. Today, live from Everett, Washington. It's been a beautiful spring here. For those who have traveled to the area, know that typically in the springtime it's very rainy here, but we had record-setting highs in the 80s, and it's well welcomed. So we're having a good year here. The presenters are myself, Richard McFadden. I'm the product manager for the electrical calibrators, and I am located in Everett, Washington. I have Paul Roberts with us. Paul, would you like to say hi?
Yeah, my name is Paul Roberts, and I'm involved along with Rich and some of our colleagues in new product development, and I've been involved in electrical measurements for the majority of my career. So I'm helping Rich out today pass on some of that experience to the audience.
Paul, and we're very pleased to have you with us, and thank you for your time today. Okay. Couple notes on the webinar today. This webinar is voice over IP only, and so unfortunately you won't be able to speak. There are a large number of attendees listening in, and typically we get some microphone feedback or unmuted microphones. So just to kind of keep the background noise down, we do the voice IP only. So if you have a question, there's two ways that you can ask. One is through the chat window, which we'll be monitoring, and also the question and answer window. You can ask a question. As we move through the presentation, feel free to ask your questions as they come up, and we'll be taking pauses, or if it's a very good question pertaining to the topic we're on, we may pause and address that at that time. There will be, after this webinar, we'll be sending this material out to you, including a couple of application notes that we'll be mentioning in the webinar. Feel free to share this material with any associates, and also there'll be a recording that if you want to view it at a later date or pass it on to somebody else, you can do so. Let's get started. This is an exciting webinar. This is the first time we've given this one, and as part of the Back to Basics series. I thought it was very important topic when we talk about basics of metrology. The things that I have the pleasure of doing is going out and builders with customers like yourself to gather information on how the products are working. Sometimes we get to do sales calls or technical calls. One of the things that always come up when we visit a customer is questions on cables and leads. A lot of the times we walk into a laboratory and the first question they have is they want to talk about a potential problem with the type of measurement, such as, hey, we're making this high resistance measurement, but we can't get the measurement to stabilize. Is there something wrong with the problem? And 9 times out of 10, you can walk over there and just evaluate the cabling situation, and within a couple minutes have it solved. And a lot of the times when product issues are sent to our service center, the first questions we ask, much like the questions a computer service center would ask, hey, is the instrument plugged in? We ask, what type of leads are you using? Are you using shielded leads or low thermal leads? And so today we want to share a lot of that information with you. It covers mainly precision measurement, but with that, these practices can be used for what I'll call non-precision measurement as well. And so when talking about precision measurement, typically we're talking 6.5 digit or higher DMMs. We're talking about transfer measurements, calibrating the calibrator. But I just mentioned we will be talking about some lower end DMMs as well, and some of the functions that go along with that. One of the things I'd like to lead into, no pun intended, is what can you need before you start the work. You look at your cabling setup, you need to make sure it's considered as part of the entire calibration setup. And what are some things you should be thinking about when you start looking at your leads? One, you want to make sure that they're safe. All leads that you'll use have some sort of maximum voltage or current rating, and so you want to make sure that it's going to be safe for the application. There is also additional what they call category ratings. These are measurement category ratings, and usually they're from 1 to 4 or 1 to 5, I think it is now. But basically, it under that test leads are conformed to, that allows you to know what their maximum ratings are, and it goes away from circuit level measurements all the way up to transformer level measurements. But it's important to know we do have an app note that I'll send out with this that covers the category ratings. What is the precision you need from the measurement? I mentioned, are you measuring 3.5-digit multimeters, or are you doing 8.5-digit multimeters? There's a big difference in the cabling requirements being performed. What you'll note today from this webinar is that when you get into the precision measurements of resistance versus voltage, there's some differences that can result in large PPM errors between measurements if the wrong cabling is used. And also the environment the leads are going to be used in. Is it a controlled environment? Are there a lot of outside influences, such as magnetic fields, electrostatic fields, for instance? We'll discuss today. Things that I'd like to mention as well is in the world of precision metrology, that you want to make the simplest connection as possible with the amount of connectors or adapters or leads, and also the same metals, which we'll talk about a little bit, the problems with dissimilar metals making precision measurements. But the rule of it is make it as simple as possible. Two helpful resources that some of the material came from today. One is an application note on how cables and connectors impact measurement uncertainty. This is available on our website. Great bit of knowledge on some of the types of measurements and what we recommend for cabling. A book that was about 20 years ago, I believe. There were editions of it. This is philosophy and practice, and I'll tell you, I read through this book recently on a trip to China, and it is just amazing the information that is in here. Very practical, well out. So you can obtain this book on Amazon. It runs about $60 US, but a great resource for many questions that you may have. Okay, when you look at the test setup, when you're calibrating a DMM or doing a transfer measurement or whatnot, there's a couple things that you have to be aware of when precision measurements. This diagram that I show on the slide here is a basic schematic of all the different errors and the error sources that could potentially affect your measurement, and it varies from the type of measurement that you're trying to obtain, but just a couple notes here. So you definitely see that there's lead resistance there. So depending on the cable type, it could be high, it could be low. It's also lead inductance, which we'll talk about in terms of AC, also capacitance that could be in there. Dielectric absorption, when you run through a lead, and also susceptibility to electromagnetic interference. Is the cable shielded? And so what the point here is that there's a lot of influences and a lot of things that need to be considered when making precision measurements. I'm going to 3 types of common cable leads here, just to kind of give us a basis as we talk through the recommended measurements. The first one is patch cords. Cords are typically used for either calibrator to DMM connections or calibrator to calibrator connections, or even in some senses transfer measurements. But basically, they have the same type of connector on both ends, and so that's spade lug or banana. It's a way to connect 2 instruments together. Telescopes are going to be with a point on them that allows you to take direct measurements, precise measurements, by putting the probe somewhere on a circuit board or a circuit, or even in a sort of uh, I'm trying to think of instances that somebody told me about the five-way binding post. Some of these test probes you can actually stick into a five-way binding post. That's one of the 5 ways that you can make the measurements. That's not recommended, but it is one of the ways. And coaxial cables. So we'll start off here. These types of cables are easy to connect and manage. They do typically have good shielding that can reduce your measurement errors. Now, typically you'll find is that they come with 1 of 3 types of plugs, and there are many various types of ways that you can order these or obtain these. Some with N-type, 1N, B, and C on the other, or SMA type, but are adaptable. And so you'll see one of those 3 types of connections. Typically, our high-end calibrators, such as our 5790, which is our AC measurement standard, we have an N-type plug out the front of that device, and that allows for direct, easy connections to other devices. It's ideal for oscilloscope calibration and RF calibrations and applications, which we'll talk about. Typically, these the coaxial cables have about 50 to 75 ohms. When you look at the specifications for these, you will want to note what the resistance is of the cable, because that could play into your measurement. I mentioned they're typically shielded, and there's different types of shielding that they use. Some of them have PVC, some of them have PTFE, which Paul will talk about here soon, but usually good shielding with these types of cables. The downfalls is that typically these coaxial cables can have high capacitance, potentially reducing the signal at the end of the cable. As an example, most common types of cables that are on the market is the RG58U, has 50 ohm RF impedance, and typically it is about 90 picofarads per meter, and so just in that you need to consider when you're looking at these cables. Came in. What is the recommended cleaning material, and how often cleaning coaxial cables or the mating plane? I have some information on that. Paul, do you have anything off the top of your head you'd like to share on that?
Yes, very, very quickly, Rich. Right at the very end, we do have a single slide which gives you some information on all of the resources that are available regarding RF and microwave cables. This is really DCLF section here. And we really haven't touched very much on some things like connector care and cleaning, which are really important in the RF and microwave world, where you would be looking at cleaning the insides of the connectors and making sure that they are also clean, no dust or debris inside, they're not damaged or broken in any way, and they are clean, and we would use isopropyl alcohol, or isopropanol as it's sometimes called, clean them out to get rid of any dust or contamination. Use air out of an aerosol can. Don't be tempted to use a factory airline, because that often has oil in it from the compressor, that's pressure of the air. And mechanical tolerancing using gauging is very, very important, but that's a whole discussion of one single webinar in its own, and we point you towards the app notes and also some other online on-demand web seminars that are covering all that sort of stuff in much more detail. So you see that towards the end, and if you are interested, I suggest you delve into those resources that we'll show you there. If we have time and you have more questions, then we'll do our best to try and address them today. Otherwise, I think the best way to leave it for now.
Great, thank you, Paul. And then just a couple considerations here for using coaxial cables. So coaxial cables actually specify a bend radius, and the reason for that is because inside like I mentioned, there's some sort of shielding, and typically, um, I think done as a kid the paper clip, as where we bend the paper clip back and forth until it actually snaps. Well, it's the same thing that's happening inside these cables. So all the cables that we ship, for instance, with our 5790 BU instruments, we have a precision coaxial cable that we supply with that, and we ship it in a box where it never goes past that radius point, bend point. So just keep that in mind as you're evaluating these cables. If you have a cable that's shielded that you've used forever, it might be due for replacement. So keep that in mind as well. One thing about, and we're going to go through the shielding techniques here in a moment, but just note that with braided type cables, they're not as effective um, as a foil shield. And so there's some numbers that we have here from our training seminar stating that about 80 to 98% in coverage from outside influences using the braided shield versus a foil shield, which typically gets 100% if it's in good condition and hasn't been broken inside. Probes, we're not going to cover too much on test probes today, but did want to note that they're easy to obtain, very common. The one thing here is, not all test probes are the same. When you do your research, you could run to Home Depot or wherever your local electronics store is and get a pair of test leads, no problem. But and they'll do the job. But just know that there are high quality test leads out there, some with higher safety protect features, such as the Fluke here that has the shield that retracts, and also you can that shield by turning that tip of the lead. And so there are differences, but these are typically used by DMMs, and they give you a way to make measurements. So make with these types of measurements, these touch measurements, it is very handy to have different accessories depending on the types of measurements that you're trying to make, such as it's hard to see there, but basically there are clips that you can clip onto a wire, such as they call them alligator clips, or even precision alligator type clips, which can pinpoint a spot on a circuit or such. But you want to make sure your leads are capable of working with those types of accessories because they really do make your job easy. Okay, patch cords. Now this is going to be more of the type of cord that we use for calibration of DMMs and transfer measurements and such. There are a couple types of patch cords here, like the banana plug that you see on the left. Those are neat because you can stack those. So if you have multiple connections that you're trying to make, those usually can be stacked on one another pretty safely. Then there's the non-stacking type, that release the plug patch cords. With the one shown there on the left is a one with a non-retractable sheath, and basically you would stick that into the front of the calibrator, and the reason that sheath there is to prevent, as you're retracting it out of the calibrator, say you had 1,000 volts on that wire, there would be no chance of coming in contact with that. So it is definitely a safety feature. There's another type there that I show that is spring loaded, that allows you to retract that. And the reason for the type is sometimes the receptacle that you would plug those in may not be fitted for a sheath. And using this type, it allows you to plug it in, and the sheath retracts so that you can use it with that instrument. Things to point out with these is that volt and category rating are sometimes hard to read, and so take the time to do the research on the lead before you use it. If it's in question, it could save your life. Expensive lead sets are typically not shielded, so like the the pics show there, those non-stacking banana patch cords, this would not be shielded. And so what we find is, as I mentioned, a lot of times when we go visit customers, making high resistance measurements with those types of leads, and you'll find out through this webinar that that probably isn't the best use of those leads and can lead to measurement errors. So I guess the message here is using the right lead for the right job. There layer that holds the banana plug in to the lead. What we found is sometimes those can loosen over time. So basically that metal section there, it's got a natural flare to it, the way it was designed, and that's the only mechanism that holds it secure to the terminal. And so times after a lot of use of putting in and pulling out, depending on the quality of the lead, that can loosen, and it in this case can cause measurement errors. So just know that could be a source of measurement errors if you're using older leads. One last thing I'll mention is dissimilar metals can cause thermal EMFs. And we'll go through this in its own slide here briefly. It says, as the test lead which is connected to the DMM terminal are deep and access is limited, hence how to do the cleaning of the test lead terminal. We'll get near the end here, as Paul mentioned. That's a very good question. We'll mention a little bit on lead care. Okay, great. So I'm going to turn it over to Paul, and Paul's going to talk about measurement influences.
Hey, thanks, Rich. Yeah, we're going to talk about a number of influences, and then talk about what we can do in terms of the leads we might use and the way we might use those leads to of some measurement problems. But one thing you really should think about first is trying to eliminate the sources of any potential problems and interference, rather than concentrating on the best possible lead to avoid the influence that's there. We should do both. We should have obviously used the best possible lead, but really should make sure that we choose the right environment and conditions such that we don't have the influences in the first place. And that said, I also want to mention that in today's session, we really only have an opportunity to touch and scratch the surface of some of these issues, and therefore maybe another session in the future where we delve into some of the issues in great depth and look more at the lead configurations other than the lead types themselves. So I might just consider one or two issues and leave it a little bit short, perhaps, for some of you more experienced folks, because time is limited and there is just so much information that we potentially could convey. We to try and get the most effective information to start with before delving into too much detail and running out of time to cover adequately all of the different parameters of volts, amps and ohms that we really need to cover. So that said, here we go. Let's talk about this radiation, which is usually an influence from something outside our measurement that might be present in the environment, some kind of electrical noise that comes from power transmission lines, the lighting that we have in the room, motors, maybe cooling fans, aircon units, like that in the lab. I can remember a case myself in one of our labs where the aircon that was in there to cool down and regulate the temperature in the lab, the actual cooling fan motors were actually located in the lab rather than outside, and sometimes we actually noticed on some very sensitive measurements that there was some influence when they kicked in and we got a glitch. In these days, it's a little bit less a problem nowadays with our LCD monitors, but the CRT, cathode ray tube monitors, that we might have had with the computers, which rely on magnetic fields for deflection and big old power supplies, could cause a problem. We have, of course, nowadays, the communications equipment. We have to be a little bit careful about the siting of our wireless LAN access points, and of course, cell phones in our pockets are some other problems that really, in many laboratories, the use of cellular telephones and similar transmitters discouraged or banned completely because they can produce some quite high signal levels very, very close to the instrumentation. And even if you're doing low frequency DC work, if there's something there that could cause some of that RF energy to be rectified, it can still cause problems with EC measurement. So be very careful about those kind of things, because what happens is those radiated, either radiated electric fields or radiated magnetic fields can get into our measurement circuits and cause unwanted effects. And typically we're talking about voltages, higher voltages causing electric fields, and higher currents causing magnetic fields. And some of those magnetic fields actually come from the measurement and circuits themselves, rather than from instrumentation, which might have transformers, line mains transformers, and so forth. So clearly some kind of shielding would be good to mitigate the effects and eliminate the radiation either exiting in the first place. In other words, we have the instrumentation with screens in it, and most well-designed instruments have appropriate screens inside them. It may not be the case with some of the lower cost and cheaper models. And of course, as Rich has said a number of times already, the use of shielded leads is an obvious thing that we can do to provide some immunity, and also to prevent radiation. If we happen to have a lead set up where we might actually radiate some magnetic fields or electric fields from the measurements we're making. So as a company involved in these kind of precision measurements, we do, as Fluke, provide some appropriate leads which look to improve the shielding, and also some of the other effects like thermal EMF and so on, with both banana plugs and some of those spade type of leads, which you'll see will be more appropriate in different kind of situations. So as I said right at the beginning, while the shielded wire will help with the problem, there's certain things that you can do to just be aware and be careful of. So I've noted some of those down there on the side, which is the very obvious one about the layout in the laboratory. Keep and mains wiring in the lab out of the way, run it through some grounded metal conduits, and be careful about the use of those fluorescent fixtures. LED lighting is becoming more common nowadays, and some of that LED lighting is somewhat better. Other lighting also uses high frequency converters, so you have to be, again, careful. Most of the good lighting fittings, of course, have grounded metal enclosures, which help. And as already hinted, the design of an instrument such as a precision calibrator or DMM would probably have a well-shielded power supply within the instrument, but some of the more general purpose instruments, things like perhaps power supply units you might have on your bench for use during some tests, which may just be used in your precision calibration, but it happens to be there on the bench because you've used it in a previous test or something, might be a source of interference. So be careful. Think of the test you're down. Do you need all that instrumentation there? And perhaps a few tests. One way to check if you've got some interference problem from radiated pickup is to make some measurements of some low-level AC signals of a few millivolts and see if you have any problems. If you've got interference coming into your circuits, make a measurement like that, the chances are you'll get a result that's wrong, and the result will be wrong by having a lot higher than you expect, because the unwanted signal is adding into your measurements, particularly if the bandwidth of the system that you're DMM that might have a 1 megahertz bandwidth, and you're getting some pickup from a high frequency fluorescent fitting, for example, where you might have frequencies running in there perhaps at 10s or 20s or hundreds of kilohertz. That would be with your measurement bandwidth. They'll add in and make your answer wrong, typically higher. So that's a good way to see if there's something that you switch off that makes the result go down and get closer to the real answer. That's where your problem's coming from. Eliminate it, and also think about using some of the leads that we're recommending today. Another comment here that I'm making towards the bottom of this, the last point on that slide, is it's lead layout that can be a problem as well. If you've got any current carrying conductors that are part of your measurement setup, be radiating a magnetic field that will be getting across into your voltage or current lower sensitive current measurement circuits by some kind of magnetic induction. So if you're in that circumstance, for example, you're making a measurement using a current shunt, the current input to the shunt and the voltage output from the shunt, you could get crosstalk between. So be careful about your layout and appropriate use of the types of leads that you use for that kind of situation. At one of the and really this is what I've just been talking about in some kind of diagrammatic form. And the issue here is that you get magnetic coupling loops. If you have a large loop in your measurement lead, that's much more susceptible to getting pickup than if it's a tight loop, because the magnetic field induces a voltage in the wire. Now, if those two wires are very, very close together, the voltage will be introduced into the high and into the low, which means that the differential, which your measuring instrument is sensing, is more or even zero. So that's why using coaxial cables where the current, the conductors are running coaxially, one inside the other. Now that gives you a good electrostatic shield. It also gives you a good magnetic shield. Nice twisted pairs where the wires are twisted very closely together to minimize that loop area will be a benefit as well. And if you can arrange that your leads are at right angles to the magnetic field, that's even better still, because the magnetic field has to cut through the loop in a perpendicular direction. So if you can orient the leads so you minimize the crossing of the magnetic field. If you remember the right-hand rule from your day back at school when you were taught the basics of electromagnetism, the left-hand and right-hand rules for generators and all good stuff, you'll remember that things have to be at right angles to get the maximum effect. So if you can make sure that the other 90 degrees, that there's no crossing of your loop and the magnetic field, then all to the better. So you do, well, as I said, magnetic pickup can be reduced by reading the area of the pickup loop and actually reducing the magnetic field intensity. In other words, taking the interferer further away, reducing it in a way such that you can shield it and so on. Use twisted pairs rather than separate test leads, and particularly so with higher current. And that's got high current flowing in it. If you twist the leads together, you reduce the radiated effect that might be picked up in some sensitive parts. Likewise, the converse happens in reverse. If you've got a sensitive measurement, twist the leads together. Better still, twist them and put a shield around them. Well, keep the leads away from anything that might cause interference to be picked up and wrangles as well. Also be aware that the same thing can happen with the instruments themselves. If you stack instruments on top of each other, you may actually be bringing into close proximity a radiation source inside an instrument with a sensitive circuit inside another one. And the typical example is a mains transformer, line frequency 50-60 hertz transformer, which is radiating, and if it's not particularly well shielded, it will radiate through the instrument case into another instrument. So be careful when you stack instruments on top of each other. Those kind of things can happen. You might want to put them by the side or move it around. You can easily see when something is going on because you can see an effect, and just take a minute or two to think about it and perhaps reorient the instrumentations and see if you have a problem. Of course, many of us know that one of the best ways to shield something magnetically is to put a closed magnetic path around whatever the source is, for example, a transformer, and if that magnetic circuit has a effective resistance, lower reluctance to the magnetic field, the magnetic field will constrain itself in that material and not radiate as strongly outside, and that's why we make use of this alloy of nickel and iron that everybody knows as mu metal. So mu shielding is a good thing to use in these circumstances. about grounding. Grounding is another area where we can get ground loops, and we can get voltages appearing in our measurement circuit when we think they shouldn't be there, because there are often ground currents flowing around where we make our connections. Sometimes those connections are obvious, like we've actually plugged in our line cords into different parts of our electric circuit where the ground tension is slightly different because there's some heavy loads running. Something big is plugged in, that's got a big load, and if there's leakage current running down the ground wire, that can actually cause the ground to move up and down. This is a common effect. The effects we don't really have time to explain to you in great detail, other than that currents flow in ground leads. Those can couple into our measurement circuits by various effects, and there's some good practice there that we're describing on this slide, where you can plug things from the calibrator in the unit under test into the same receptacle, very close, keeping them on the same circuit. Don't use different circuits that come from different breakers in the box. Don't have them on different phases if you have a 2 or 3 phase system. Keep those connections short as possible, which means the impedance will be as short as possible. Make sure that you use, where possible, shielded or coaxial or twist pair type cables that we've been talking about. But there's often a temptation to break a ground loop by disconnecting a grill earth cable, the safety earth, and that's never a good idea, because while it might break the ground loop, it does put you at risk of electric shock. So breaking or cutting the wires or using those cheater plugs is not a good idea. There are much better ways to avoid ground loops by doing some of the things we've just talked about, rather than putting you and your staff at risk of electric shock. Next slide is really an indication now with some pictures to show you what we've been talking about, where we've been talking about braided mesh, foil, twisted pairs, and twisted pairs covered with foil. So it's a bit of a summary to say, well, okay, there are these different types of shielding and different types of cables that can help us to avoid some of this pickup and signals that are unwanted getting into our measurement circuit, and also avoid some of the currents that might be flowing in our measurement leads to get out and cause problems as well. Now, in here, you'll see we've sort of put some pros and cons and some ratings for the type of shield and the effect of shielding. And like most things in metrology, there's no absolute rights and wrongs. And when we're talking about shielding rating here, it's sort of a rule of thumb, you know, how much shielding, and is it good from an electrostatic point of view, is it good from a magnetic point of view? Clearly, those foils and the building is really a Faraday cage, so that's good for electrostatic B, either static electric fields or varying electric fields, and the make a very tight loop. In other words, have 2 conductors running together, either very close side by side, concentrically in a coaxial connector or in a twisted pair, helps us with the magnetic shielding. So you can see there, most of those cables are pretty good, and some are better than others for electric versus magnetic. You can see there they all rate against each other, and of course sometimes you would be better off with a coaxial cable than a twisted pair, and we'll attempt to explain some of that later as we go through talking about the different measurements. In the topic is I just want to touch on instrument guarding, because a guarding is pretty much shielding by a Faraday shield, and you can see the picture of the instrument there in the diagram below, representing a shield that's being surrounding all of the sensitive measurement circuits to avoid problems from electrostatically coupled or electric field coupling. And as I said, if we use mu metal as well, we can do a good job of shielding from magnetic effects. But there's an effect where it helps dramatically, and that's in what we call COM mode. This is where voltages will appear effectively on both high and low side of our measurement for reasons usually associated with capacitance in mains, transformers, and things like that. And by using a guard terminal connected to that metal shielding, we can encourage any currents that might be flowing in. Eyes would be our low lead and cause volt drops to appear in the resistance or inductance of that low side lead. Those currents can be diverted away harmlessly through the guard and not appear in series with our measurement circuit. And the guard terminal is the one usually appearing on the front panel of the instrument. Sometimes you also have a local or remote guard switch, a hardware switch on the front panel, or perhaps it's one of the controls you can operate through the user interface or remote programming of the instrument, where that terminal can be connected to and allow you to drive the guard from the instrument, from the outside world going inwards or the inside going outwards, depending whether it's a source or measuring device. That's a very complicated subject, and there are lots more information in the calibration book and some of the app notes that we really don't have time to talk about in great depth today, but just a little snapshot that it is something which is often misunderstood and misused. So I suggest you take a look at some of the information that's available in those other resources. Other area, which is an issue principally with measurements involving DC voltage, either because we're measuring DC voltage, or DC voltage is what is actually measured in something like a resistance measurement, or maybe measurement involving current shunts where the output is a DC voltage. And that's this effect where temperature comes into play. If you have dissimilar metals joining together, there's an effect which generates a voltage. Seebeck effect is the one that we know of. Obviously, there are some other effects as well. And that's the effect that we make great use of effectively as thermals use to sense temperature. The problem is we don't want a thermocouple in our precision measurement situation here. We want to avoid them. So we avoid any of these junctions of dissimilar metals that could be, for example, when we have two different metals that are joining together because our leads have to terminate into the Bernard jack, or they have to terminate into the spade lug. That spade lug then has to connect onto the terminal and so on. So there are junctions there, and by choosing appropriate materials for our leads, we can avoid those dissimilar metal junctions, which is why in the calibration instruments we provide from Fluke, we use tellurium copper, which is one of the lowest EMF generating metals. You see there's some examples on the right hand side there. If you take a piece of copper and other material and put them together, how much EMF is generated metals, and you will see in some cases there they are quite a significant number of microvolts, particularly if you're looking at oxidized copper. So that's why we want to make sure any copper leads we use are nice and clean. And a few microvolts can be very, very significant in precision low voltage measurements, where we might be measuring a volt or a few hundred millivolts or tens of millivolts. Then the microvolts can be really significant. So we have to be careful, usually to avoid nickel plating at all costs, and be going towards copper or gold plated or some of these other tellurium plated leads. So the problem there is we have to be very careful, but we're all about the temperatures as well as the dissimilar metals. So if we can keep everything at the same temperature, that reduces the effect. So we need to be careful that we shield our terminal connections from drafts. If we handle the leads to make the interconnections, then give them a while to cool down from the heat of our body temperature at about 38 degrees C, or that's over 90 or 100 degrees Fahrenheit. That's pretty warm, and it can easily give us a problem that takes a few minutes to go away. So let's handle the end of the lead where the sensitive part is, hold the lead a bit further down, and be aware that, of course, even the joints are a problem, and the lead terminates at the end between the physical metal wire of the lead with the material of the jack or connector is, and then the terminals. So keeping the terminals at the same temperature by putting insulation around with them, minimizing drafts in the environment and so forth, are all good mitigation effects that we should follow. It's back to you now for some of these comments.
Excellent. Thank you, Paul. I wanted to note one on that last slide for the dissimilar metals. I think a area that really comes into play is when you're in a laboratory and you're kind of doing on-the-fly testing or measurements, precision measurements, and you may have a new device or such, and you look around you and it has a connector type that maybe you don't have a specific cable for, and you start digging for accessories, you start digging for adapters. That's when that can become a problem. So a general rule of thumb we have here is that in all of our laboratories, we keep those separated so that it doesn't accidentally grab one and it'll lead to an issue that we're not even paying attention to. So just a couple of thoughts I'd like to share there. Any questions up to this point? Paul, there was one question that came in that was really great. When you were talking about the electromagnetic fields, air conditioning is pretty common in laboratories, but also fans, force fans to drive the air conditioning. Would be concerned at any point if there were like ceiling fans that were driving the air above the lab. I mean, what would you consider if you were setting up a laboratory in that situation?
Right, those are the sort of things. I mean, the types of electric motors, whether they're AC motors, DC motors, whether they're brushless or so forth. There's two different aspects. One is when a motor kicks in, if there's a glitch, which might disturb DC measurement, because you get a kick and you see something happening or a resistance measurement, and that might also disturb an AC measurement rather than something where a more continuous effect that would cause electrical noise that adds in to an AC measurement the way that I described. So one of the things we've always done when we've been setting up our labs is we've looked for these kind of things before we start any serious measurements with a new setup, is to go in there and, as I kind of hinted, one of your most sensitive measurements, and just turn on and off these systems and see if you can detect an effect. So, you know, have the system shut down, set your measurement up, say 10 volts or 1 millivolt out of your AC calibrator at hertz, and then turn the fan on and see if the reading changes. Does it glitch when you hit the button to turn the fan on? Does it stay changed? Those kind of things are the sort of techniques. At the end of the day, apart from sort of thinking about it up front, often there's not much you can do apart from just actually having a full evaluation in those kind of, you know, turn it on, turn it off, see if you can detect a difference, sort of on the brute force measurements.
Okay, perfect. That. Okay, now we've got about 12 minutes left here, so I'm going to go through this a little bit quickly so we have time for questions. But I did want to provide you with some measurement guidance on different types of measurements. So each of these slides pertain to a certain type of measurement, and we're going to start with voltage, DC voltage. For performance, we recommend the use of a low thermal, low EMF cable. Like Paul mentioned, DC measurements are more adversely affected by dissimilar metals than AC, simply because thermal EMFs are no concern in AC. With cables and connections, there are not many error sources from a DC measurement. And so if you have this diagram below, that's probably the simplest connect, and with the least amount of errors, just based on what DC is and how it's measured. And so what is typically a measuring device has a high impedance, which is the RL, the load. Usually of 1 mega ohm or 10 mega ohms are graded for a for EMM DCV inputs. Any DC loading effects will usually be negligible because the lead series resistance, so the R lead, which represents the resistance of the lead, is very low compared to the measuring device input impedance, and that's around 0.1 or 0.2 ohms. If you take that the resistance there and times it by 2, what you'll see is that with a 1 mega ohm input with them, you typically or could get 0.2 ppm error. And the in summary is a pretty stable and error-free measurement. But
Rich, may I just leave in there for a second,
yes,
please?
Paul.
Apologies, Pin, but there is one thing that occurs to me there. We illustrated that with a calibrator, but if, for example, you were using a voltage divider, the voltage divider would possibly have quite a high output impedance of tens or even hundreds of kiloohms. The situation might be rather different, but in that case, your measuring device would be the dominant impedance there. So again, watch out if you do have that situation, and just think a little bit more about what the overall impedance and loading effect is, and leads may or may not be part of that.
Thank you. It was a good question that just was, and somebody caught on to this. The question was, is there an order that's followed when performing electrical calibration? The reason we just mentioned DC is first because typically it's common to do the DC calibration of a DIM or a device first, and that's because many of the circuits that operate inside the calibrator are such in the DC circuitry, and so it's good to make sure that's in check first. But the calibration manuals for each device vary, but typically DC is started with. The resistance, low resistance measurements. This is a problematic measurement if not if you use the correct cabling. And so what we recommend is that you use a copper wire or spade lug securely tightened to the binding post. This you're not going to want to use the banana jacks for. So we typically recommend either a copper wire, as shown there, wrapped around the terminal, or a spade lug connection. Now this is when as we just talked about dissimilar metals and such, one time to stabilize. This one, some leads themselves, they have a soldered connection, and also have dissimilar metals. There could be issues, but just take your time with this measurement. Using 4 terminal techniques minimize the effect of cable and connector lead and contact resistance. So we're going to discuss that in a moment, 2 and 4 wire comp, and it does help with the measurement. When we're high resistance, so much different than low resistance. This is one area where we would want to use a larger cable, typically a banana plug. And the reason for a banana plug in this case is because the DMMs that are being tested typically do not have a spade lug connection. So it's acceptable to use these types of cables. One of the things that you're going to know or want is the cable must have very high insulation resistance. They call it, some call it PTFE, and that's an abbreviation for a very long word that I'm not going to embarrass myself trying to pronounce. But basically, you want a cable that has greater than 10 to the 12th ohms of insulation resistance. Now use low voltage wire coated with other materials for high resistance applications. A recent customer visit, just to share a story, they had problems with the resistance measurement stabilizing. Walking over to their laboratory, looking at the instrument, I could tell right away what the problem was, and basically they were using those patch cords without insulation and without a ground plug, and the measurement was just all over the place. As soon as we plugged in the ground and also used the right cable, the measurement stabilized right away. And the takeaway was to invest in a good cable for that measurement. They spent probably a good 5 hours with tech trying to figure out why the instrument wasn't stabilizing. So we do sell these cables. If you're interested, I can help you obtain one, but just send me an email after the webinar. The considerations for high resistance measurements is electric absorption, settling effects, and voltage memory. We won't go to those in depth today, just because we don't have the time. They are influences that affect this measurement.
May I comment there?
Yes.
We should avoid the use of PVC type insulation leads and those single patch cords here and go over to a good PTFE insulated cable because it really is what you need for the higher values of resistance.
Thank you, Paul. Okay, so 4-wire ohms. This is a great feature, and when we're talking about resistance measurements, this is something that you should know is a feature you can use with our calibrators. Basically, a 4-wire technique is a way of eliminating the lead resistance in a measurement. And so what you see there on that figure 1, this is directly out of the application note that I'll send along with this webinar, is that if you were just making a resistance measurement, as shown in that figure 1, you have some errors associated with the lead resistance. And depending on the cable that you're using or the lead, it could be significant. And so this 4-wire that allows you to source the current measurement, but then take a separate measurement or sense the resistance or voltage across the load to give you a resistance measurement that really does not account for, well, accounts for the lead. So it's not even paying attention to the resistance of the lead, so it's not included. So it's very a good method for making resistance measurements. Wire method, when there is not a 4-wire method available, basically this method allows you to use jacks on the DMM as shown there, but you have 4 connections at the calibrator. This is a mode that you have to turn on our calibrators, but effectively it's the same type of principle as the 4-wire method, but with connections. Application note, as I mentioned on this, and I'll be sending that along with this webinar. AC voltage, we're going to run out of time here, and I apologize, so I'll go through this pretty quickly. And after the webinar, if you have any further questions, please feel free to reach out. But voltage AC, basically the big factor to consider is the cable capacitance. You want to keep the cable capacitance as low as possible, recommended below 50 picofarads per meter. Source and voltage is at the millivolt levels into the higher input impedance of electronic voltmeters. There may be a problem with excessive noise, and this is due to the lack of shielding. So shielding is very important on AC measurements. The AC can present many errors if the wrong cabling is used. And this is due to the air sources associated with AC, such as inductance, capacitance, resonances. And just that as you go up in frequency, say above 100 kilohertz, it can easily produce more errors of 0.1 or even 0.2%. So the way here is use high quality shielded twisted pair or capacitance coaxial cables. We mentioned a couple things on high frequency, but this is a great diagram. In mind, compare this to the DC diagram that we showed a few minutes ago. You can definitely see that there are more error sources just due to the physics of AC in terms of capacitance and inductance, and so those need to be considered when making AC measurements and also selecting your cables. For current, there is a little bit different aspect you need to take when evaluating current versus voltage. Number one that I'd like to just mention, because it's kind of a safety thing, is making sure you have the right cables for the amount of current that you're trying to source or measure. This can be a big safety concern, and so correct selection is important. Low-level, high-frequency current measurements subject to large errors called by leakage impedances. And I know it's hard to see probably, but those diagrams here show some of the capacitance in the line and also the leakage impedances that can occur But the takeaway here is that you want to use shielding around your cable. So again, shielded cable is good for this application, and the use of the guard is also very important if the cable has it. A quick diagram on what we just talked about. You can definitely see that there's leakage resistance and cable capacitance in here. And another diagram shows where guard connection connects to the or is in the line here, and then also where it would connect to in the calibrator. Paul, could you talk about the scope calibrator and the RF calibrator?
Yeah, and I can do that quite quickly, because I think in again, pun intended, the scope of this particular session, there's a great deal to say, because in oscilloscope calibrations, there can be quite a key and tedious process, because there's lots of different measurements to make, but in principle, it's quite simpler than some of the other measurements, because we're typically dealing with voltage. The level of precision on oscilloscope measurement not as demanding. We talk in percents or tenths of percents usually, rather than parts per million. So we've got a lot of different parameters, but not as much precision, and we have to be a little bit careful when we get to the higher frequencies involved with some of the bandwidth measurements involving hundreds of megahertz or nowadays gigahertz frequencies, and rise time pulses for the scope rise time measurements, where we're really into the RF and microwave world. And to cope with that, the design of the dedicated oscilloscope calibrators, such as you see there at the top, or the multi-function, multi-product calibrators with oscilloscope calibration options, can't take care of some of that stuff, because the 9500, for example, uses active heads to deliver the signals directly to the oscilloscope input, thus avoiding the issues with long transmission lines and long cables by making that direct connection. The multi-product calibrators that have oscilloscope calibration options typically don't go up so high in frequency with their level line outputs for bandwidth calibrations or the speed of the fast edges. So cable connections are okay, but we do recommend and provide really good, high quality precision coax cables, as Rich mentioned right up front, and good quality connectors. Even though BNC is not usually recognized as a metrology grade RF connector, many oscilloscopes use them right up to the gigahertz or so. So we have to be very careful and provide good quality BNC connectors for use with our scope cal options. So if you're going to substitute any other cables or use any other cables for oscilloscope calibration, be very careful, and would recommend that you don't, unless you procure some really good precision, much more therefore expensive cables to do that with. We do have some more resources available on the topic, which is we have an app note on oscilloscope calibration, which I would recommend you take a look at as well. So in a sense, it's easier. Many of the things we've talked about already with of course, apply to oscilloscope calibration. RF calibration is yet again another level of complexity, and we again don't have time to talk about that in this more general section, but do have lots of help and assistance. I know some of you were interested in and asked questions about connector cleaning, connector care on. Take at some of these application notes and best practice guides that we're showing you here. They're all available from the Fluke Calibration website. You can download the PDFs. They're online web seminars, which I've put together, talking specifically in depth about these topics. So you can go and take a look at those and delve into those areas in much more detail. And I've recommended 3 app notes and a couple of the web seminars on this particular slide.
Thank you very much, Paul. We're at the end of the seminar. We do have some questions that were asked that will stick around, if you can stick around to answer. And if you can't stick around, thank you very much for your attendance today. One thing I'd like to note that there are classes available here at Fluke that go through metrology, all the way from basic hands-on metrology up to very advanced hands-on metrology. And so if you're interested in those can be found on our website. Also, as you leave the webinar today, you'll be given a chance to provide some feedback. So if you would like to be contacted for any assistance with your leads, or if you'd like to get some suggestions, we can have a person come out and speak with you. Please give us a feedback you would like to be contacted on that form. Okay, so we're going to answer some questions here, some great questions. There's a question on which leads are plugged in first when using a 2-wire ohm meter and a 4-wire resistance source. Great question. Paul, do you want to take that on?
Yes, right. So the question is, which leads should you plug in first? Well, the answer is no, it doesn't matter which way around you connect them, because yes, if the meter sort of has its 4-wire sense, you connect 2 leads first. It's not actually going to get its measurement circuits together, as it were. It won't read properly until all 4 wires are in place. But usually the instruments, if they're credibly designed, they come from a good manufacturer, there won't be any problem with having circuits operating an open circuit, and effectively the instrument will sit internally in a situation where its circuits don't get stressed and there isn't any recovery involved. Some instruments do apply quite high voltages or generate quite high voltages when making resistance measurements. There are some dedicated resistance measuring instruments that actually work slightly different from all described, where they source current. They actually source voltage and can source potentially high voltage, high resistance measurement, because the higher the voltage you use, the greater the current that flows, and therefore the lesser the effect of any leakage currents that might be present. So that's something which could be an issue, and it could be a safety issue. But there is another effect, and that is if we're making measurements at lower voltage levels, which typically means lower resistance values, what for those thermal EMFs? Now, instruments have what is known as offset compensated ohms, or ohms, where on-off current or reversing current is used as a technique to overcome the effect of any thermal EMFs. That's a lot. If not, then you are sensitive to the thermal EMFs, and of course, be careful which leads you connect and how you connect them in terms of handling becomes important. The current leads aren't sensitive, the voltage leads are. So if you have to do anything first, connect up the sense leads, but being careful not to touch them or handle them excessively. Then that need the time to stabilize, and then go ahead and connect the current leads. So that's my sort of rather two-handed question to two-handed answer to that particular question.
That's a great response, Paul. Thank you. And that kind of leads into the next question here: how to test the cable? How does the cable installation for high voltage? There are a couple ways, but one of the common ways is Fluke actually sells insulation testers, and so where would measure the leakage of the lead. And so I believe the Fluke 1557 is one. And so if that's a desire, you can use a product like that to measure that insulation.
May I please, Rich?
Please. Yes.
Which is something that I think we probably should have mentioned earlier, which is cleanliness and contamination of leads. Not only in terms of the leads that we have in our labs, and some of these single type patch cords can get grubby and dirty, and if they've got even a poor to moderate insulation resistance, if they get grubby around the ends, then that dirt can actually form across the end of the lead, and effectively a loop of dirty, sort of grubby material that may attract excessive moisture. It will represent the leakage path between high and low around the insulation. And some of the unit under test items that get returned for calibration in the Cal lab, we might have a nice clean environment, but the users may have a somewhat less clean environment. So the instruments that get returned for calibration might be a bit grubby. We have to be careful. If that's the case, we might want to recommend that leads are actually cleaned and some instruments come back looking very grubby and black and oily, and that's possibly a situation where the users might need to be aware of the cleanliness issues, or we might need to give them a little bit of a cleanup to make the leads don't, we're calibrating the instrument, and okay, part of that is the lead, but those leads will be too dirty to make a decent measurement. So again, the isopropyl alcohol might be needed to clean any of that contamination off any areas of the leads that might degrade the high resistance measurement, particularly for those high resistance insulation meters. And if you do want to check out the lead and check if there's any, what should we say, leakage, you really want to do a job, then you could always wrap the outside of the lead in foil and make a measurement between the conductors and that foil and see if there's actually a detectable leakage resistance.
Thank you. That's really good information. Okay, I fear there's a ton of questions here and a lot of great ones. We're not going to have a lot of time to go through them all, but I do want to answer your questions. Do me a favor, if your question was asked today and it did not get answered, please reach out to me, rich.mcfadden, rich.mcfadden, MCFADDEN.com. And you'll have my email when I send out this material, but I would love to answer your question. And some of these questions will have to have follow-on questions to me to understand the application a little bit more, but they're really great questions. With that, thank you again for attending today's webinar. Next month, we have a live chat with an electrical metrologist. We'd love for you to attend. It'll give you an opportunity to have a live discussion with a metrologist and ask these questions. So have a great day wherever you are, morning or night, and we look forward to seeing you in the future.